Okay, let's start talking about the OS principle, part 2. In part 2, we will discuss the basic process scheduling and some basic memory management technique. In that part, we discuss what is the thread and process, and we also discuss the synchronization problem between threads. Okay, and here we will continue to discuss the process and threads, okay, and from the point of view of the scheduling, okay, and the life cycle of this process. Thread execution usually consists a cycle of CPU and I/O, okay. So every thread or process, they are continue looping or change the operations between CPU and I/O devices, okay, and this sometimes we call it CPU burst. That means in this particular time period, the process use CPU to execute its instruction, and I/O burst. That means in this particular time period, this particular process or thread is using the I/O devices. Okay, and here the I/O device maybe disk, maybe keyboard, maybe or other input/output devices. Okay, so a process is changing its resources or its execution among these two type of devices or resources. Okay, use some of the use CPU for a while and then waiting use a particular I/O devices. Okay, so the overall system throughput of a computer system should be able to increase if when some threads is in their CPU burst, while the other I/O devices are used by other threads. Okay, so the overall system throughput can be increased because not all the process they are waiting for the CPUs. Okay, so when the process is in its CPU burst, they should have other process. They are using those available I/O devices. Okay, so all the system resource can be utilized in some way simultaneously and not sequentially. So, but if we did not schedule the system properly, then it's possible all the process waiting for the same resources. Then the whole system throughput will be decreased. Okay, so the scheduler or particularly the CPU scheduling is very important in the sense that it should be able to select the right process or thread to run. Okay, so the mix of among the usage of these devices, okay, include the CPU in a situation that they all get busy in most of the times. Okay, so that's the whole point of the scheduling. Okay, okay. So if the current thread did not finish its CPU burst, but it already run too long, okay, then sometimes scheduling for reason of fairness or to avoid infinity loop or abnormal behavior of a process, most of the modern operating systems allow the scheduler to preempt the running thread. Okay, if it use CPU for too long, okay, then the particular process will be suspended and the CPU will be reassigned to others to avoid waiting process. They are waiting for CPU need to wait too long. Okay, so if a scheduler is allowed to preempt a running thread or running process and reassign the CPU to other thread or process. This kind of scheduler, we call it preemptive scheduler. Okay. In the other hand, if the scheduler is did not allow to avoid to preempt a running thread, this kind of scheduler is called non-preemptive scheduler. Okay. The objective of scheduler is to select the next ready thread to use the CPU. Okay. And the decision to make to select a new thread to use CPU usually happen or occur in the following 4 situations. Okay, the first one is that when the running process become waiting. Okay, that means the running process usually is try to use an IO device, okay, and make a system call. Okay, so this kind of in the time the running process voluntarily release the usage of the CPU. Okay, so it's a non-preemptive behavior. Okay, it's not operating system took off its right to use CPU. Okay, and usually this is triggered by the running process issue system call. Okay. The second place is that when the running process was switched from the running state to the ready state. Okay, so usually this is because the running process use up all its time quantum. Okay, so by time interrupt, the operating system take over, then preempt, suspend the running process and assign the CPU to another thread. Okay, so in that time, this is a preemptive activity. Okay, and by the time expiration. Okay, the next case is when a waiting thread switch is state from waiting to ready. Okay, this usually happen when a device finish its an I/O completion generate an interrupt, so the operating system was interrupted and the running process was temporarily suspended, and the operating system changed the state of the waiting, the blocking process from a blocked state to ready state, because an I/O completion means a particular thread which is using an I/O device, and the I/O device finish its work. So an interrupt generated, an operating system took over, get the result from the I/O device, and so the blocking process will become ready again, because then, okay. And then in this time, after this operating system service finished, it may return back to the previously suspended originally running process, or select a new process, a new thread, or select a particular thread from the ready list. Okay, so in any way, if the selected thread is not previously running thread, then it's become a preemptive, okay, activity. Okay, because the highest priority thread, if the system using priority schedule, the highest priority thread may not be the originally running process. Okay, maybe it's the process which just come out of the blocking, become ready. Okay, so we don't know. depends on the priority between these two. Okay, so that's the last case is that when the running process terminates itself, okay, finish all the works. Okay, so it again it is a non-preemptive activity because that's voluntarily to release its usage of the CPU. Okay, so usually in this if this fourth situation happens, then the CPU scheduling need to be involved and to select the next thread to use the CPU. Okay. After the selection of the next process or next thread is made, another module in the operating system we call it dispatcher. Okay, was involved by the operating system, and the objective of the dispatcher is to make this selected thread become being executed by CPU. Okay, and to do that, we need to first we need to do the context switching. You need to switch, restore the context of this selected thread back to its previously suspended state. Okay, and then switch from kernel mode to back to user mode and jump to the proper location of the user process to restart the thread from the last suspended point. Okay? And the time between a dispatcher was involved to take stop one thread and start another thread. We call it the dispatching latency. Okay.